All right. Good morning, everyone. How's everyone doing? Big class today. 8 people. All right, send me an attendance note. We'll give you credit for being here right at the start. All right. Questions so far? I want to finish up talking about processes and then talk about the exam.
What kind of stuff are we gonna see about the processes on the exam?
Did you look at the topic study guide list on Canvas?
Nope, but I will now.
Okay. Basically, high level notion of what fork does, and the process interactions from bash. So using a control Z to suspend a process, BGFG to run it in the background, foreground, using an ampersand to run it in the background, and the kill command, and just the fact that PS is a command for looking at process status. Not a lot of details on any of that. So that's on the first page of possible topics.
Okay. Well, yeah, I'll go through that. Thank you.
Okay, yeah, and we'll talk about it when we get to it today also. Um, and what I want to talk about, the first part of today, is definitely not on the exam, but it is definitely stuff that you will encounter down the road. And I guarantee you that whatever you get out of seeing it in the next 20 minutes or so is going to help you down the road. These are sort of strange concepts, and if the first time you encounter them is when you're expected to write a program that uses these, it's going to be that much harder than if you sort of think about them now, and then next year when you're at a university you encounter these again. Well, it'll be the second time you've seen it. It'll be a little easier to grasp what's going on. And so I want to talk about IPC, inter-process communication. And this is the idea that, we've talked about fork. We know that we have a main program and it's doing something. And at some point it can make a call to fork and create a clone of itself. And these two processes are identical. If we want at some point, this new process could make a call to exec, and exec will change this process into some other process. So it'll start doing something else, right? It'll read the code from some other executable file and start executing that code. And in bash, when we say something like, date pipe into cowsay, right? This pipe is a way to connect commands together. And what's it really doing? When we say date, the date command generates some output. When we say cowsay, it reads some input, and our cow speaks that input. And so if we said date and we took the output of date and put it in a file, and then we said cowsay, but we said let's take the input of this command from that same file, then our cow tells us what the date is. And we can do that without an intermediate file by using a pipe. We can say date pipe into cowsay. And now what we're saying is execute this command, but standard out of this command, instead of going to the display, should go into this end of a pipeline. And the other end of that pipeline should feed standard in of cowsay. And so this connects these two commands together, and we get the same result as if we had a temporary file. but without a temporary file that we have to delete later. And so we can think of these pipelines as, you know, some kind of conduit that you can put stuff in one side and read stuff from another side. And that's basically what's happening here. When we say date, we're saying, hey, I want standard out of this command to go into this pipe. And cow say, I want standard in to come from this pipe. And now these two commands are linked, and whatever output this generates goes into here, comes through the pipe, pops out the other side, and hey, cow say is reading from that, so it goes into standard in. So that's the basic pipe mechanism, and it's you know, what makes that pipe symbol work in Unix. But it's part of a more general concept, which is having processes communicate with one another. Because this and this are, you know, separate commands. They're both running at the same time. They're separate processes, so they have, you know, their own memory, their own code, so on and so forth. But we're trying to share information between these. And so this business of how do we send information from one process to another, that's what we're going to talk about right now. And it turns out it's done through a pipe. And this pipe symbol in bash to connect two commands together is really just a way to get bash, the program, to use this low-level pipe mechanism to create this communication conduit, this channel. And so the command we're interested in, not surprisingly, is called pipe. And pipe comes from chapter 2 of the manual pages, which means it's a low-level, sort of a system-level call. And it's called with an array of two integers, which here is called pipe FD. That's just the name of the array. And it returns an int. But mostly what the pipe command does is it loads values into these two elements of this array. So calling pipe does a few things. It creates a pipe, so you have this thing down here. And it creates a way to talk to each end of the pipe. So there are these things called file descriptors, right? They're integers that basically correspond to input or output ports, usually of a file. But standard in is file descriptor 0, standard out is 1, standard error is 2. And anything I write to file descriptor 0 goes to standard out. Anything I read from file descriptor 1 comes from standard in. So when I make this call to pipe, a conduit is created, and a pair of file descriptors are assigned. And if we called pipe with, you know, pipe FD as its argument, so we set something up like this, and we call pipe with an argument of pipe FD. Here's what happens. This end of the pipe, pipes are unidirectional. This end of the pipe, which is the output end, is accessible with whatever file descriptor is in pipe FD bracket 0. And the input end of the pipe, the end we write into, is accessible with the file descriptor that's been saved in pipe FD bracket 1. And I can use a write call, right? Write is the low-level version of printf. I can use write to write into pipe FD bracket 1, and whatever I write will go into this pipeline. And if I read from pipe FD 0, I will read in order everything that's been written into this pipeline. So let's just spin some code to play with this. Alright, so here's a pipe demonstration. So what I want to do is the following. I want to have my main program, and I'm going to do a fork and create a child program, and I want to have a way to communicate between these. In particular, I'm going to have the parent process, the original main program, send some piece of information to the child. Alright, so I'm going to make my array of file descriptors from my pipe. So I'm going to call pipe with an argument of pipe FD. And let's just see what these file descriptor values are that get created by the call to pipe. So let's just do this. And let's just leave it at that for now. Let's just create a pair of file descriptors for the two ends of a pipe, and let's just see what those file descriptors are. And we're not going to do anything else. We're just going to print those out and exit. And guess what? My file descriptors are 3 and 4. And so we know that there's standard in, standard out, and standard error. These are, the high-level things. When we say fgets, we can use standard in as the third argument. Those are file pointers. But they're tied to these low-level file pointers, if you like, which are called file descriptors. And standard in is file descriptor 0, standard out is 1, standard error is 2. And those are the 3 file descriptors you always get when you run a program. So when we created this pipe, using a call to, pipe, the system created 2 new points of communication and assigned file descriptors to them. Well, the next available one was 3, and the next one after that was 4. And so that's why those 2 ends of the pipe have file descriptors 3 and 4. But if I had opened up a file before I did that, then those descriptors might have been, 4 and 5. But we don't really care, what the numbers are here, because we're just going to access these using pipe FD bracket 0, pipe FD bracket 1. And the assignment of those goes like this. Right? Pipe FD bracket 1 is the end that you write into. Pipe FD bracket 0 is the end that you read from. So we've got our pipe created. We've got a pair of file descriptors that we can use to write to or read from this pipe. Let's make a child process. So fork will create the process. So if PID is 0, if the fork returns a 0, it means I'm the child process. Let's print a message. So I'll say I'm the child and I'm waiting for a message. And what I'm going to do is have the child receive a message from the parent and then print it out. Alright, so to do this input from a file descriptor, we need to use a function call named read. So read is also chapter 2, it's a low-level system call. And read takes 3 arguments: a file descriptor, a buffer, and a number of bytes that are available in the buffer. So it's kind of like a low-level version of fgets. But the order of these is also different. So file descriptor, buffer, and the number of bytes we want to read. So I'm going to say read. We want to read from pipe FD bracket 0. And I'm going to make a buffer called buffer, or let me call it child buffer, and I'll just leave 120 bytes available in that buffer. So and then I'm just going to print the contents of that buffer. And then the child's going to exit. It's just going to do a return. And you know, this is the main program of the child, so when I say return, the child will exit. Alright, so let's send a message to the child. So we'll prompt the user to enter a message. We'll read a message from the user, and then I'm going to write this message to the pipe, which means the child should receive it. And so I'm going to use a function call named write, which looks very much like read. File descriptor, buffer, and number of bytes to write. And so I write into pipe FD bracket 1. And I'm going to write out buffer. And I'm going to go ahead and write the full 120 bytes. Why not? And then I'll just print a message saying, parent has sent the message and is exiting, and I'll say goodbye. Alright, so you got the basic setup here. We create a pipe, which is, you know, this conduit that has two endpoints. And we're going to do a fork, but when we fork, both of these processes will be identical, other than the PID, which means they'll both have access to this same pipe. Which means if one process writes into this end of the pipe, the other process can read from that end of the pipe. And so in this case, the parent's going to ask me to type something in. I'll type something in, it will write it into the right end of the pipe. And the child, meanwhile, will be sitting here trying to read from the pipe. When the child receives a message, it'll print out the message you got, and then everyone will exit. Alright, so we run this. Our pipe's descriptors are still 3 and 4. My parent said, enter a message. Meanwhile, the child said, I'm the child waiting for a message. And both of these processes share standard out, so they're both sending messages to the screen. So if I say this is a test, the parent sends the message and exits goodbye, and then a little while later the child receives the message, this is a test, followed by a new line. So this is inter-process communication. And it's the low-level, you know, C-code version of what's happening, part of what's happening when we pipe two commands together. And so a couple of things to note in the spirit of, you know, saving you time in the future. it's tempting to say, how many bytes do I want to send? Well, let's just use string length of buffer. And that's actually not a good thing to do. I forgot string, but that's okay. So let's say I want to send the message hello. If I do string length of that, that's going to give me a string length of 5. If on the child side I decide I'm just going to read, if on the parent side I decide I'm only going to send 5 characters, all I'm sending is HELLO. And on the child side, it will read HELLO. If I try to use that as a string, I might have a problem. Right? I really want to send 6 characters because I want to send that null terminator as well as the HELLO. And let me see if I can get into trouble here. So if I send HELLO, the child receives the message HELLO, new line, and a bunch of X's. Right? The reason is HELLO followed by a new line has a string length of 6. 6 characters, HELLO, new line. If I use string length to send that, I'm only sending those 6 characters. I'm not sending the null terminator. And the child, when it reads from the pipe, it's going to read HELLO new line, and that's all it's going to load into this child buffer. And if the child buffer happens to have some other stuff in it, that stuff will be sitting there where the null terminator should be. And when you run this, you get strange business going on. And so if I'm doing this, I'm always going to want to include the null terminator. And that'll make things work better. That's probably only vaguely making some sort of partial sense, but trust me, you'll come back to this sometime later, and it'll make more sense. All right. But this is a pipeline for sending information. So final things to note on this. First of all, pipelines are unidirectional. There's one end you write into, there's another end you read from. I cannot write into this end and read from that. If I want two-way communication, I would make a second pair of pipes. And, I would have this process write into whatever's at index 1, and this process read from index 0. And I would treat this pipeline as going in that direction. So you can do two-way communication between processes. And this is fantastic, right? Because these two processes are doing their own thing. They have their own independent execution once the fork has happened. But I can still share information between them. I could send instructions here. I could ask for status updates on whatever it's doing, and so on. The other thing we can do, and this is also, not on the exam, but there's a function called dupe2, and you'll definitely see this one down the road. Dupe2 is used to duplicate a file descriptor. And what I can do is by calling dupe2, I can say, hey, this file descriptor 0, which is standard in, I don't want standard in to go to this anymore. I want standard in to go to, say, this. Well, let me do it the original way. Let's forget about that. I want standard in to go to this. Or I can say, hey, standard out, which was file descriptor 1, I don't want standard out to come from file descriptor 1 anymore. I want it to come from whatever this file descriptor is. And so now we can create a pair of processes with a pipe. We can set up with dupe2 an arrangement so that standard out of this process goes into this end of a pipe. And this process we can set up so standard in of this process comes from this pipe. I did these backwards. Do you know what I mean? I'll do it clean. So I can have bash, and the person says I want to do date and pipe it into cowsay. Okay, so bash executes a fork. And it does an exec on date, so that now this process is executing the date command. Bash also does a second fork and does an exec on cowsay. So now we've got a process running cowsay, we've got a process running date. But before these execs happen, it creates a pipe before the fork. So there's a pipeline here. And before the exec happens, it makes a call to dupe2. And it says, hey, take standard out and send it into this end of the pipe. And for this process, before it makes the exec, it will say, hey, let's do a dupe2 so that this file descriptor takes the place of standard in. And then it does these calls to exec to basically change these processes into a process running date, a process running cowsay. But when this process is running the date command, guess what? Standard out is connected to this end of a pipe. And so when the C code inside the date command says, print out, DEC, because that's the month, it doesn't go to our display, it goes into this pipeline. And the cowsay command, when it does an fgets from standard in, instead of reading from a keyboard, it's going to read from this end of the pipeline. And it's going to read a DEC and the rest of it, and then it's going to print out a picture of a cow saying, whatever it read from standard in, which will be the date produced by the date command. That's how this pipe works. That's how it's implemented under the hood. You definitely do not need to understand this for the final. But in courses at a university, you'll probably write code that does this kind of thing, but does it from a low level using forks and execs and dupes and things like that. So you've seen it once. You'll see it again. All right, let's talk about the final exam. So this is an 11 o'clock a.m. daily class, so your final exam is Wednesday, 11 o'clock to 12:50. It's an hour and 50-minute exam, unless you have an extended time allowance. If you have an extended time allowance, then it ends, at whatever the extended time is. It will be structured similarly to the way the midterm was. So there'll be on Canvas a final exam assignment that will pop up, and you can open it up and it will list, a series of questions. And you can download that or read it on Canvas, your choice. And it will be a series of questions. You'll write up answers to the questions, save them in a file, save that as a PDF. And then upload that PDF by the deadline, either 12:50 or the extended deadline, if you have an extra time allowance. And if you have an extended time allowance and you upload late, Canvas will say it's late. Don't worry about that, right? I know what your time allowance is, and I'll deem it late or not late based on the extended time. So don't worry about Canvas's red letters saying late.
Do you expect it to take us the whole hour and 50 minutes?
Very possibly, yeah.
Okay.
Let's see, if we have slip days by the end of the term, will they be turning in extra credit? No, they won't, unfortunately, and I debated doing that, but I would have to announce that up front if I was going to do that. And I don't think I want to monetize people's slip days, so I'm probably not going to do that in the future either, but it's an interesting idea. But yeah, if you have slip days, they're just, bragging points.
Can we get those bragging points in writing?
You can print yourself a certificate that says, I finished 224 with all 4 slip days left.
There you go. Add it to the
There you
wall.
go. Yeah, totally. All right,
Can
so
we get trophies overkill?
I could do like participation trophies for the whole class. That would be so awesome, right?
There you go. All right.
Let's see. All right, so final exam. Same setup as the midterm, basically. So again, make sure that you have a way to write code where the editor is not, changing your indenting, making things uppercase, stuff like that. Plain text editor, VI works great. If you don't like VI, Notepad, Notepad++, WordPad, anything like that. If you know how to make Google Docs or OpenOffice or Office behave and actually take what you type verbatim, that's another option.
I believe if you turn off the autocorrect settings in Word, it works pretty well.
Okay,
And you can save it straight to a PDF from there.
that would be cool. I've never had luck myself, but if that's all it takes, that's awesome. All right, so let's see. And yeah, I'd like your code written up, typed, not handwritten, because I have to grade these. But if your handwriting is very legible, you can write code by hand if you want, but it's going to be faster to type it, I would think. All right, so topics. I posted a study guide on Canvas yesterday. Refresh Canvas if you're not seeing it. But the course basically breaks out into 3 major chunks, right? One chunk is Linux, which is, the stuff we do day to day when we're living and working in a Unix environment. So basic commands, ways of interacting with files and processes and compiling and all that kind of stuff. The second is Bash programming, which is, in particular, the language constructs of a Bash script. And so you've done, some of your programming assignments in Bash. That's what this is about. And then the third is C programming, which is, programming assignments you've done in C. So I'm planning to just go through this in order, but if there are particular questions that you have that you want to talk about, we can do this in whatever order people want. And, I'd rather answer particular questions than just talk for the next, day and a half. But I'll just start going through this in order and interrupt me if you like. So basic Unix commands, right? So these should be the things that you've been using, every time that you start working on an assignment, an ODP, a PA, whatever, right? You should be doing these commands because you're working in Unix. So echo, which shows you a message, cat, which displays the contents of a file, VI, which edits a file, CP, which copies a file, MV, which renames or moves a file, RM to delete or remove a file, LS to see a list of files. I'd like you to know ls-l at least, just because it's so useful, right? And -l basically just gives you a long listing. So it adds all these extra columns of information. WC, which tells you the number of lines, words, and characters in a file. Date, which shows you the current date. And other commands. So any of the commands, you can just look at your history. And if you've got like a history of 5,000 commands, right, there's a good study guide probably for what commands you should know. All right, you definitely should know Git. And mostly you want to know add, commit, and push, right? Plus general concepts. So Git's a way to control source code, and there's a repository, and it keeps track of changes and older versions and so on and so forth. And for us, we're also using a remote repository, GitLab in our case, and we can make copies of our repository on GitLab by pushing. So you should definitely be very familiar just through experience with git add, git commit, and git push origin master. In the beginning of the quarter, when we set up the 224 repository, we had to do a git init to make that first repository, and then a git remote add origin to link it to GitLab. And it wouldn't hurt to just jot this down on a note card what the exact git remote add origin statement was, but what you should know is, when you do git init, you create a repository, right? When you do git remote add origin, you link that repository to a remote system like GitLab. When you edit a file or create a new file or make a change to a file, you can say git add in the name of the file, and that moves it to a staging area. When you say git commit, the things you've moved to the staging area become part of the repository. That makes the changes sort of official. And when you say git push origin master, that pushes the changes you've made to your local repository over to the remote one. And that's pretty much it for Git. Standard in, standard out, standard error. So these are these three streams that we always have kicking around in the background of programs. Standard in is where most commands read from. It's where fgets and getcar will read from. And it's by default usually the keyboard. If you run a program that's reading from standard in, it's probably waiting for you to type something and hit enter. Standard out is where output goes, like when you say printf. And by default, that's usually the display. So if I run a program here and it writes something to standard out, I'll see it pop up here. And standard error is another output stream. It's usually by default also the display, but it's actually a separate stream. And so we could write things to standard error, and technically they're going somewhere different. They're going through a different pathway from what we write to standard out. Now, by default, both of those pathways end on our display, but if we redirect our output using a greater than sign, greater than redirects standard out, but not standard error. So if I run a command and I say greater than file name, everything that's written to standard out goes into that file. And before that happens, the file is truncated. If I do two greater than signs, then whatever I write to standard out gets appended to the bottom of a file. And if I do command less than file, then standard in is redirected to take input from that file. So it starts at the beginning of the file and it reads from it, and that's what feeds standard in. So that's I/O redirection. And the other way we can change standard in and standard out is by using pipes. So this is this whole business of, command 1, pipe into command 2. Whatever this sends to standard out goes into standard in of command 2. Command 2 won't read from the keyboard, it'll read from the output of command 1, which doesn't write to my display, it writes to the input of command 2. So they're piped together. Alright, quotation marks. So in Bash or Linux, we've got three types of quotation marks mainly. Double quotes seemingly don't do much. So for example, if I say echo hello, it echoes hello. If I echo quote hello, it echoes quote hello. If I set x equal to hi and I echo $x, it says hi. If I echo quote $x, it still says hi. So double quotes don't seem to do a lot, with a couple of exceptions. The first exception is double quotes group things together. So for example, if I say vi, this is fun, I'm editing a file called this. And if I try to quit, it tells me I have 2 more files to exit. When I said VI, this is fun, VI announced it had 3 files to edit. This, is, and fun. So I can edit this, I can edit is, and I can edit fun. And you know, I just edited 3 files, fun, is, and this. If I edit this is fun inside quotation marks, it's a single file. And that file is called this is fun. And if I do an ls, I have 1 file called this is fun. So that's one thing quotation marks do for us. They let us group things together. So instead of calling VI with 3 arguments, I just called it with a single argument, this is fun. The other things they do is, if I echo quote star, I just get a star. If I echo star, bash will eat that star and turn it into a list of files. Oh, it will turn it into a list of files in the current directory. So echo quote star just echoes a star. But echo star without quotation marks tells bash, hey, instead of an asterisk, I want you to find every file that matches that pattern in asterisk and replace this with that list of files. Well, every file in the current directory that matches asterisk is just ABC, and so it echoes ABC. So that's one thing that quotation marks do for us. The other thing, single quotes are almost exactly the same, except this business of taking a variable and replacing it with its value by saying $. If we use single quotes, that doesn't happen. If we use single quotes and we echo $X, we just get $X. Other than that, single quotes kind of work the same way as double quotes. If I VI hello world with single quotes, it's just a file called hello world. Alright, back quotes are the ones that are really different. So if I say something like date, that shows me the date on standard out. If I say x equals date, it just sets x equal to DATE. But if I set x equal to back quote date, that says run the date command, and instead of sending the output to standard out, basically replace this with what was sent to standard out, and so x is set equal to this big long string, and so now x contains what the date was when I ran that date command. And it's just an assignment statement. But before that assignment is made, date is executed, and the contents of the output are used as the right-hand side of that assignment. So backquotes are the way that we capture output from other commands and do things with them in bash. And make sure you know how to use backquotes. I've seen people using like $paren instead. Make sure you know how to use backquotes, because you'll see them. Alright, what is a shell? So, you know, bash is the shell we've been working with. Loosely speaking, you can think of a shell as a program, in this case a program written in C, which lets you type something. It does a few things, right? It displays a prompt, and the prompt could be, you know, a number in brackets, it could be a username followed by a $, but it displays some kind of prompt, and it waits for me to type. And when I type something, it will do something in response. If I type pwd, it will figure out what my current directory is and show me what that directory is. If I type x equals 12, it will do something internal to say, hey, if this person asks for the value of x, remember it's 12. If I type a command that bash doesn't know, like date, it will look for a file named date somewhere that has executable code in it. And if it finds it, it will run that file's contents, and in this case, you know, it finds a file called date under the bin directory, and it runs it, and that program shows me the date. And I can say which date to see what date's going to do, and date's going to execute a file called /bin/date that basically figures out the current date and time and prints it out in this format. And so a shell is mostly a way to interact with files in the operating system, to run commands, to look at information, things like that. And the shell we've been using is bash. There's a bunch of shells available for Linux. Bash is the one we're using. And one thing you should know about bash is this .bashrc file. So in your home directory, there's a file called bashrc, or there can be a file called .bashrc. And if that file is present, every time that bash begins, it will read instructions from here and perform these instructions. And so, for example, there's a variable I'm setting up called histcontrol, which says, hey, if I type the same command 5 times, don't save it 5 times in my history list. Just save it once. There's a command here which says, how many lines do I want to remember in my history? There's a bunch of alias commands down here. When I want to scrape the attendance chats, I have a script I wrote. This is a bash script called clean attendance. It's sitting under my home directory files, useful commands, teaching. I don't want to have to be in that directory or type this every time I want to do an attendance scrape, so I have an alias called clean. And if I say clean, that's a shortcut for running this script. And that's an alias I use a lot. And so I put that alias in my bashrc, and every time that I start a bash session, all of these aliases get set up. So for example, I have an alias called clean.
So you're just basically just writing alias, whatever your variable or your command was, and then what you want it to do?
Yeah, so alias, the name of the alias, equals sign, and then the thing you want it to be equal to.
Okay.
Again,
That's
with no
one thing I've never
spaces.
really played with.
They're really useful.
Yeah, I'll have to check that out.
Yeah. So we can put whatever we want in our bashrc. You can put something in there that, you know, reads welcome messages, or, you know, whatever. And then,
So
yeah.
could you set up an alias, like, because every time I come in, I go to my main directory, you know, and then if I want to go to the CSE directory, can you just set up an alias, just say, like, you know, go, and that goes to your new directory?
Yep, absolutely.
Or whatever. Oh, okay.
Yeah.
That's kind
So
of
you
cool.
can set go equal to cd, blah, blah, blah. And I probably have some of these. So if I say Kura, it changes my directory to this big, long, horrifying path. And then also runs a file in there.
So on your main directory, before you log into the server, can you set up an alias to just do, like, the SSH command?
Mm-hmm.
And then I know we talked about it way in the past about bypassing the password, but
Yeah. So you can set an alias that would say SSH username at linuxengrcs.com. And if you go into your .ssh directory, you can set up, on your Linux side, you can set up an authorized keys file that lists the keys of users who are allowed to come in without a password.
oh, okay.
Yeah. And I think there's some video chat about that you can probably find in the video index. And that's a nice space saver. So for me, I just SSH $Linux, and it hops in there. Or I can do $test, and it brings me into my test account.
It's funny because it seems like a lazy thing, but it's not lazy. It's the, you know, work harder or work smarter, not harder. You know.
Yeah, yeah.
It's just kind of cool.
Okay, and someone set up a macro, same idea. So you press one button and it logs you in. That's definitely cool. You know, it's one of those things. It might save you a few seconds, but if you log in, you know, several times a day, or, you know, several times an hour, like I do when I'm teaching, it adds up. All right, processes, which we've been talking about. Main things to know, just the low-hanging fruit. Use an ampersand to run something in the background. Control Z to suspend a job. BG or FG to resume a job in either the background or the foreground. Kill to kill a job, which you can kill by % job number or process ID. And PS, just know that PS is a command that lets you see processes, and know that there's a billion switches you can set on this. I won't ask you to know what those switches are. So basic interaction with processes through Bash. And fork, the only thing I want you to know is two things. One, it creates a clone of the current process, and two, the return value is different for the parent and child process. Child, it returns a 0. Parent, it returns non-zero, which is the process ID of the child. So we've talked about a lot more than this, but those are the only things about processes I need you to know for the exam. And general concepts of process. Every time you execute a command, it runs as its own process, and processes have process IDs. And most processes are created by other processes. If I'm running bash and I say date, the date process is created by the bash process. And all these things can be traced to like a grandmother process, which we call a init, which creates all the other processes. All right, so we'll continue this tomorrow, but please take a look through this and see if there's particular things you really want to be sure we talk about. We can talk about those first tomorrow, and then we'll just continue talking about Linux, and then review Bash programming and C programming. All right, shoot me a note on the way out, attendance ping, and have a great afternoon. I will see everybody tomorrow.